Arun?
Yeah. Hello, Ramki.
Hi. You can hear me, no?
Yeah, I can hear you.
Okay, thank you.
And yes, slides are also coming, projecting. Okay.
Yeah. Let me check that. Yeah, it was okay.
Not able to see you.
Hello?
Hello.
Okay, okay, okay. Are you able to see?
At some point, I think you give the permission for me to share my slides.
Yeah,
Yes, sir, I'll
we'll
do
do
that.
that.
Yeah, fine. No problem.
So we wait for 5 minutes so that people log in, then we start.
Yeah. I sent the link to Sanjeev last night. Also to Yogesh. Also to Gautam Sheet at Izer.
I've sent all them to the individual. I think we can start. Okay, very good morning to all of you. We are going to start the CX, the 6th Professor B.M. Anand Memorial Lecture. Actually, this is a prestigious lectures from the physics department. It was held previously 5 times in an offline mode, but due to the pandemic, this could not be organized in offline mode. So this time we are organizing in an online mode. Actually, this lecture was instituted in the name of Professor Bal Mukund Anand, who is the first head of the department of the physics department of this independent India in Punjab University. And Professor Manmohan Gupta will introduce you to the little later about Professor B.M. Anand. And today's speaker with us is Professor Ramakrishnan, presently the director of Tata Institute of Fundamental Research. So before we start the actual program, for 3 minutes, actually we'll start our customary Punjab University anthem. So let us be silent for 2-3 minutes.
बोला क्या प्ले करने के लिए सुना आपने एंथम
तमसो मा ज्योतिर्गमय तमसो मा ज्योतिर्गमय तमसो मा ज्योतिर्गमय ज्योतिर्गमय तमसो मा ज्योतिर्गमय ज्योतिर्गमय तमसो
विश्वविद्यालय तेरी शान और शौकत सदा रहे मन में तेरा पंजाब विश्वविद्यालय तेरी शान और शौकत सदा रहे पंजाब मन में तेरा तेरी शान और शौकत सदा रहे तू है पंजाब विश्वविद्यालय पंख बिना परवाह सिखाता तू है अपना जीवन विधाता पंख बिना परवाह सिखाता समझ बढ़ाता जीवन पुस्तक रोज पढ़ाकर सही गलत की समझ बढ़ाता तेरी जय शंख बजाए पखरी तेरी शोहरत तेरी शोहरत तेरी जय शंख बजाए पखरी तेरी शोहरत तेरी शोहरत सदा सदा पंजाब
Okay, welcome back. We have a lot of students also both in the YouTube and in the in the
Professor
Cisco
Mehta,
web.
just check the thing. There is lot of echo and it's multiple broadcasts. Please get it checked.
Okay, is it okay?
Slightly
I
better,
request all
yes.
of you to please mute.
You can unmute all the people so that
Yes, you can start, Professor Bell. Please unmute yourself.
all students are requested to write their questions on the box in the chat box here in Webex or also in the YouTube. At the end of the talk, we'll take the question. Now I request Professor Suryakant Tripathi to tell few words about Department of Punjab University.
So,
Professor
good
Tripathi.
morning, Professor S. Ramakrishna, Director TIFR, Mumbai, and other colleagues. On behalf of the Department of Physics, Punjab University, I am giving some glimpse of the physics department. The Department of Physics was established at Lahore in 1934, and after that it moved to Delhi for some time, and then to Government College, Hoshiarpur, Punjab, after partition. Subsequently, the department was shifted to Chandigarh in 1958. The department had previously received grants under the UGC COSIP program from 1977 to 83. Then SAP, that is Special Assistant Program, from 1980 to 88, and COSIST, Committee of Strengthening of Infrastructure in Science and Technology, from 1984 to 91. Since 1988, it has been accorded the status of a Center of Advanced Study, CAS, by University Grants Commission, with three major thrust areas. Those are particle physics, nuclear physics, and solid state physics, which is a unique achievement by the department. At present, the department has the strength of 21 faculty members, 2 UGC faculty, 36 assisting staff, and 2 daily wage staff, apart from postdoctoral fellows under various funding schemes, as well as project scientists and investigators. There are about 108 research students and 437 BSc Honors School Physics, MSc Honors School Physics, BSc Honors School Physics Specialization in Electronics, and MSc Honors School Specialization in Electronics students on the rolls of the department. About 150 BSc Honors School students of other departments study physics subjects as a generic elective courses. The faculty members have been honored with different awards like Meghnad Saha Award, Goel Prize Award, Sir C.V. Raman Award, Hari Om Trust Award, S.N. Satyamurthy Young Scientist Award, DAE Young Scientist Award, Himachal Scientist of the Year Award 2011, Chinese Academy of Sciences President's International Fellowship, Mercator Professorship, Homi Bhabha Fellowship, Emeritus Scientistship, Ramanna Fellowship, and many more. They have been elected for Indian Academy of Sciences Fellowships, Juliet Curie Fellowship, Alexander Van Humboldt Fellowships, DFG German Research Society Fellowship, BMFT Ministry of Research and Technology of Germany like DST Fellows, UNESCO IAEA Fellowship, W.E. Harris Fellowship, Henrik Hertz Foundation Fellowship, Fulbright Fellowship, Commonwealth Fellowship, IN2P3 CNRS Fellowship, France, Third World Academy of Science Fellowships, and UGC National Lecture Fellowship Awards. Our faculty had also are serving at various administrative positions, such as Vice Chancellors of Punjab University and other universities in the country. The department is having research collaborations with institutions like Royal Military College of Canada, Canada University of Notre Dame, USA, BNL, USA, Fermilab, USA, CERN Geneva, Bonn University, Germany, University of Beirut, Würzburg, Munich, and Berlin in Germany, Chemistry Department, City College of New York, KEK, Japan, Chinese Academy of Sciences, Shanghai, China, ICTP Triest, University of Illinois, USA, BNL, USA, Max Planck Institute, Germany, University of Leipzig, Germany, Subtech, Nantes, France, Institute for Theory Physics, Tübingen, Germany, Institute of Nuclear Studies, Warsaw University, Poland, University of Milano, Italy, JI University, Germany, JW Jewett University, Frankfurt, Germany, Institute of Nuclear Physics, Strasbourg, France, University of Surrey, Guildford, UK, University of Hawaii, Cincinnati, Virginia Tech, Princeton University, University of Antwerp, Belgium, JINR Dubana, Russia, IUC Kolkata, VCC Kolkata, TIFR Mumbai, IISc New Delhi, IIT Kanpur, Delhi University Delhi, Mumbai University Mumbai, IIT Chennai, IOP Bhubaneswar, Himachal Pradesh University Shimla, TBRL, PGI MER, CSIO Chandigarh, Jammu University, and so many other places. The department has MOU with IUAC New Delhi for joint faculty appointment and to various academic exchange programs for accelerator-based research. UGC had sanctioned 3 crores under CAS 5th phase, that was from 2015 to 2020 grant under improvement of infrastructural facilities of the physics department. Funds of around 3.5 crores for infrastructure development have been sanctioned by the Department of Science and Technology under the FIST program to upgrade teaching and research facilities. There are many achievements of our faculty members, and these faculty members have been honored with Meghnad Saha Award, Goel Prize, Sir C.V. Raman Award, Homi Trust, T. Young Scientist Award. They have been elected for Indian Academy of Sciences Fellowships, Juliet Curie Fellowship, Alexander von Humboldt Fellowships, DFG German Research Society Fellowship, and so on. The department had the honor of having Professor S. Paul, former UGC chairman, on its faculty. Professor Ken Pathak was Vice Chancellor, Punjab University, Chandigarh from July 2000 to July 2006, and Professor Satya Prakash was the Vice Chancellor, Jivaji University, Gwalior from February 2001 to November 2006. So it is. Okay. Now, Professor Bega, please.
Thank you, Professor Tripathi. The Professor B.M. Anand Memorial Lecture, it was actually
Was not audible.
You.
Professor
Speak a little
Anand
louder.
Memorial was actually instituted by the generous support from the Professor Anand's own family members and with the efforts of Professor Arun Grover, who was at the time a Vice Chancellor of Punjab University. Now I'll request Professor Manmohan Gupta, who is the Professor Emeritus at Department of Physics, Punjab University, to say few things about Professor Anand and to introduce today's speaker, Professor S. Ramakrishnan. Now over to Professor Gupta.
Good morning. Thank you, Dr. Behra, for giving me this opportunity to be part of this lecture. Although I was never a student of Professor Anand, but my brother used to be his student. So, and I used to live opposite to his place. So I had lots of stories, lot of interesting anecdotes about him. Anyway, I won't spend much time about that. But one thing I would certainly mention that apart from his meticulous effort put in to establish this wonderful department, which has produced a great scientist, most of the people are known right now. But at the same time, see, I used to hear he was a very strict disciplinarian. And if the department inculcated the experimental culture, I think we all owe to Professor Anand. my brother used to say that he was really meticulous in the lab. 2 o'clock means 2 o'clock. I think Dr. Suman Berry maybe might have been his student. And I remember that he was very particular about the use of the instruments. His discussions about vernier caliper used to be wonderful. And let me mention that because my brother used to tell me all these things. So when I joined the physics department, I try to work out, and I find that see these are simple principles, but the physics behind these simple principles is very profound. And if you master that, then I would say that you get into the precision frontier of the physics, which is the most important. Anyway, Professor Powell, B.M. Anand's contribution to physics are very well known. He was part of the Cecil Powell's team, which discovered pi meson as well as measured the lifetime of pi naught, which are very legendary contributions. And I would say that because of his experience with the emulsions, he was the professor who started the experimental physics culture in high energy physics. And Professor Suman Balaberi is there. I'm sure that they were all part of. I would also used to go to their laboratory and I would see how emulsions are used to observe particles. And I would say that in due course of time, that wonderful laboratory using emulsions, you can say, emerged into a very important area of high energy physics. And right now, the physics department, Punjab University, is in the forefront of participation at CERN experiments and Fermilab experiment and other. So they are part of the, you can say, big team which have been discovering T quark or Higgs boson and so on and so forth. So it is all because of the foundation laid by Professor Anand. And he was, see, he was a passionate teacher and a passionate researcher. The fact that when he demitted office at Punjab University, he went to USA, settled there, he kept on teaching, and he was very passionate about teaching even over there also. So I would say that in short, he was a wonderful personality, and I would say that the seed sown by him have really grown into a big tree, and I think we are all thankful to his family, which of course I used to interact with family members also. So I would say they have done a great job in instituting a lecture in his memorial. So with these few comments, I would sure that Professor Patel, Professor Suman Balaberi can add on later on some of the anecdotes. There are too much material which can be discussed. And now let me give a very brief introduction to Professor Ramakrishna. Of course, I think the rightful person would have been Professor Grover, who must have spent a lot of time with him and being experimental solid state physics. But anyway, I have to do my constitutional duty. See, he doesn't need any introduction. See, whenever I have interacted with Professor Grover, he has always told me the kind of stellar persons who are doing fundamental work at TFR. And Ramakrishnan name has always been there. I used to see his Ramki more as a popular name, and no wonder that see he was you can say graduate students at TFR, and it's very rare to see that you are a graduate student and then ultimately you become a distinguished professor and then a director. So he is so well known in the international arena in his field that he doesn't need an introduction. But uh, of course, for the people who are not familiar in this area, one must add that he has won several awards. He is fellow of the Bangalore Academy. Then he has see several countries, like he has been a regular awardee by the Von Humboldt Foundation. Pathak is also there, so must be knowing much more about him. Similarly, the Japanese society has also showered a lot of praises on him. Then there are other countries which have recognized his work. But I am most impressed. See, when they talk of low temperature, when I was studying the abstract, and the two papers are going to be published by Nature, I think beyond that, one doesn't have to give anything. We all know how easy or how difficult it is to publish in Nature, and in the present competitive atmosphere, I'm sure that it's a great achievement for the country, great achievement because of the effort of Professor Ramakrishnan to have reached at that level. And I was wondering that it's a complete new frontier where they are working. It is a fraction of a millikelvin. So low temperature or ultra low temperature means that, which is see the we are familiar as I am a particle physicist, so familiar only with superconductivity, which is 4 degree Kelvin. But this is, you can say, it is almost 1 lakh lower than that, 5 orders of magnitude lower than that. So the low temperature or the ultra low temperature of present day physics is really very, very low. I think I wouldn't like to add more. Maybe I would request Professor Grover to say a few words about him, because I'm sure that he has spent so many years together, and Professor Grover has a penchant to, you can say, observe some of the critical things. So it would be wonderful if we can add certain things about Professor Ramakrishnan, so that we also get, you can say, know about this wonderful man, who is of course director also, and doing frontline, really frontline international quality work. So with these brief remarks, maybe I would request Professor Grover to add a few things because of his long association in TFR. Thank you very much.
Yeah, Professor Grover.
So good morning, everyone. I am indeed delighted to have an opportunity to add a few words to what Manmohan has just told you about Ramki. Ramki is not new to our department. He had visited physics department once, at least once earlier, and also given a talk. So as Manmohan said, Ramki joined TIFR as a graduate student, and he is a contemporary and a batchmate of another very stellar physicist of our country, Professor Padmanabhan, who passed away unfortunately last year. So Ramki's batch at TIFR was really spectacular. It was a small batch, but each one of them emerged and grew as a top-class physicist in his field. And Ramki's batch at TIFR was such that they were not offered any graduate courses. You know, the TIFR graduate school had this hallmark that you have to go through some formal graduate courses, write exam, get some grades, and so on. So when Ramki's joined TIFR, at that time TIFR was going through a transformational stage, and to their batch there was no formal course structure that was offered to them. So the courses were taught to them as per their need or demand. So they educated each other, all the graduate students, and wherever they found that they needed to have a course, they requested and they were given. So this batch was really very special, and it produced very special physicists on behalf of TIFR. So Ramki is perhaps the second PhD student of TIFR who evolved to become the director of third in some sense. Okay, his first one was Professor B.V. Srikantan, who was directly a student of Homi Bhabha. Next, Sampath, who was our contemporary in the condensed matter department. He also served for a brief while as a director of TIFR. And thereafter, Ramki is the third one who started as a graduate student and grew up to become the director. There have been people who have been directors. For instance, Professor Virendra Singh has also joined TIFR as a student, but he went on to do his PhD from Berkeley. Professor Jha also had joined TIFR from the training school in some sense as a student of TIFR, but he had his PhD from Stanford. So amongst the students who had their PhDs from within the TIFR and grew to be the directors of TIFR, it is Srikantan, Sampath Kumaran, and Ramakrishnan. So that is one distinction that he has vis-a-vis the rest of us who are also graduate students at TIFR. So Ramki's forte has been, of course, superconductivity, because that was the topic of his thesis. But thereafter, he worked with Pobble and learned the techniques of ultra-low temperature techniques. And this ultra-low temperature techniques, there is no one like him in the entire country. You know, many decades ago, he had proposed that he will build an ultra-low temperature lab. It's a very difficult task to do it, but because it takes long and you need to do very difficult experiments, and it is not a field in which you can publish papers by dime a dozen. You know, you work for many years, build up an experiment, and then you explore something new and to establish something new, it takes a while. It's a very difficult and challenging field, but he took it up, he built up the lab, and eventually went on to have an outstanding result to his credit, and that was the discovery of superconductivity in bismuth. And that is a talk that he had given to us in the physics department of Punjab University a few years ago. So, and his talent as an experimental physicist was recognized within the TIFR system as he joined. I mean, not only he got the Best Thesis Award, he also went on to win this Satyamurthy Award of the Indian Physics Association, which is given to students who actually build up an experimental lab to explore a newer area. So in TIFR, whatever Ramki did had no past. So no wonder he was given the Satyamurthy Award. And later on, he went on to win a very prestigious award, which is given by the German Humboldt Foundation. And he has worked with very famous people. For instance, Ramki worked with John Maidosh at Leiden. He also worked with Peter Kess at Leiden. He has also worked with very well-known Japanese physicists, okay, more than once. So all that experience that Ramki gained, and he worked as equal with all of them. So all that experience he brought back to TIFR, and I was fortunate to work with him very closely from early 90s till the year 2012. So I'm very delighted that the physics department accepted my recommendation to invite him to give the B.M. Anand Memorial Lecture, and Ramki also graciously accepted it. And we are here to welcome him in the presence of Dr. Vinod Sani, who has also known Ramki equally well along with me. And we also have the good fortune of having son and daughter-in-law of Professor B.M. Anand in the audience, along with, of course, our teacher or teacher of all of us, Professor K.N. Pathak. And I don't see Vijay Jindal around. Vijay Jindal and Ramki were postdocs together in Germany for a while at University of Beirut. So Ramki is a familiar name and face to a large part of the older generation of the physics department condensed matter community. Thank you very much.
Thank you, Professor Grover. Now we invite Professor Ramakrishnan to deliver the 6th Professor B.M. Anand Memorial Lecture. Yes, Professor Ramakrishnan, now we can start.
You need to unmute yourself.
Oh, not audible.
Can you hear me?
Yes.
Yes.
Yes, sir.
Yeah.
Yes.
Okay, so I thank Professor Gupta and Professor Arun Grover for their introduction, and I'm deeply honored to give this PM Anand Memorial Lecture today. I mean, I see that Professor PM Anand was a gifted scientist, excellent teacher, and also mentor to many. I mean, this has been brought out very nicely by a beautiful biography written by Dr. Rajinder Singh. And so before I start my lecture, let me just share my slide. I hope you can see my slides. And so before I move on to the lecture, let me just recall some connection of DNR to TIFR. He taught Professor Yashpal, who was a distinct professor at TIFR, who became UGC chairman. And when he was a PhD student, he taught him at the Lahore College in the 40s. PM Anand also had a strong overlap with Professor M.G. Kimin, who was the second director of TIFR at the Nobel laureate Professor C.M. Powell's lab in Bristol. He had met our founder, Dr. Homi Bhabha, in Chandigarh when they later visited the new Punjab University campus in 1959. Lastly, but not least, Professor Arun Grover, former VC of Punjab University, met him as a NSTA student, and that made him a deep impression. And then he continued physics as his research career. Later, as a VC, he suggested Dr. Rajesh Singh to write a biography of Professor Anand. So I think we are proud that we had some connection with Professor D.M. Anand. And so today I chose a topic, to give is something which I built, we are very proud of it because it is the third best ultra-low temperature lab in the world. And when you want to build something, first question you ask is why do you want to build it? So what's so important that you want to build a system which works at a very lowest temperature? And so what's the physics which can come in this range from 50 millikelvin to 50 microkelvin? So I'm going to tell you that interest. So what are the things? So one of the questions which you ask is what is the fate of the ground state of the metals and alloys? That is an important question because we would like to know what is its ultimate ground state. And many properties like superconductivity, that is SC, quantum phase transitions, nuclear magnetism, magnetism of nuclear spins, all these happens at very low temperatures. So it is important that you have a platform to investigate this phenomenon. Then superconductivity occurs in granular form. Platinum is not a superconductor down to the lowest temperature people have drawn. But in a granular form, it does tend to show superconductivity at fairly higher temperatures from 0.6 to 1 millikelvin. Then you have very unusual superconductivity. Happens in ytterbium, rhodium to silicon 2 at 1 millikelvin. And then the superconductivity of bismuth, which was a TFR result in 2017. I'm going to talk about that later. There is also a lot of theories which seems to suggest some exotic materials like samarium boron 6, ytterbium boron 12. All of them will show superconductivity, but the mechanism for superconductivity is completely different from the mechanism which we have known so far. Then the other interesting aspect is the two insulators, lanthanum aluminum oxide, strontium titanium oxide. You take these two layers and the interface starts superconducting. And so that is another unusual results for which you need temperatures down to at least 10 millikelvin to investigate. So why do we go to lower and lower temperatures? The reason one can immediately say that there are many phenomena which occurs at room temperature because the low temperature gets vanished at the higher temperatures. So the most important one you will come to our mind is superconductivity. So everybody talked about D.M. Anand. I think Campbell Onus has the same discipline and the rigor as Professor D.M. Anand, I think. So I think this is something which is very well recorded about Campbell Onus. And once he liquefied helium in 1908, his purpose of producing liquid helium is because he wanted to study the properties of materials at low temperature. So surprisingly, he found the superconductivity of mercury in 1911. So, even this measurement is quite tough in those days because mercury is a nice metal. You need to make a thin capillary, the size of less than a micron of diameter to measure its resistance. And he showed that, it goes from about 12 milliohms to about 10 microohms at 4.2 K. So this later turned out to be a revolutionary phase transition, which is called the superconductivity. So the superconductivity, though the phenomena happened in 1911, it's only in the later part of the 70s the application started coming in because people went on to make superconductors at higher temperatures, also superconductors which can stand high magnetic fields. So the magnet, superconducting magnet started coming in the later half of the 70s. And then in the recent times, the superconducting magnet is used everywhere. Particle accelerators, the LHC, power generators, transportation, power transmission, computing, medical detection using squid, and many. And if you go to a local hospital, you have this MRI machine. The magnet is made of superconducting material, and this is an invaluable diagnosis in the medical field. So you can also use superconductor for the levitating train, which is called Maglev, operating in Shanghai for the last 10 years or so. So the applications of superconductors are vast. So the name of the game is that can we have superconductor at higher temperatures or even room temperature? Because most of these applications which I have showed you, they need liquid helium, which is an expensive material, and also we need all the cryostats and other things so that things can work with helium. So now I am going to move away and then talk about the periodic table of superconducting elements. What you see here is the one which is shaded in green are the superconductors at ambient pressure. The one which is shaded in yellow, it is either they are superconducting under pressure or in thin films or in some geometrical form. So as you can see, that superconductor is a very wide phenomenon. I mean, many of the elements are superconducting at one temperature or the other, or at one pressure or the other. There are, of course, notable exceptions. I said, magnesium. The theory says you should be superconducting and in the millikelvin temperature. The experiments say that it's not happening. At least we did the experiment down to 100 microkelvin. It just refused to become a superconductor. So let's go to a topic of today's lecture. So most of the metals have a very high carrier concentration of the order of 10 to the power of 12 electrons per centimeter. Bismuth is a unique element because it has a carrier concentration 5 orders of magnitude less than the typical metal. It is also called a compensated semi-metal. So let me just go back. So once the superconductivity started discovered in mercury, then the other materials started coming in. Many of them were in the periodic table were discovered. The ones which are at very low temperatures took a little longer time, like superconductivity of iridium, superconductivity of tungsten and beryllium, and superconductive rhodium. And that was done by Mentor more than, let's say, 40 years almost now. And then the superconductivity of lithium happened. So it took 16 years for the rhodium superconductive to appear and 24 years for the lithium superconductivity to be demonstrated. And now after 10 years, we have the superconductivity of bismuth at ambient pressure. So the work has been mainly done by my former student, Dr. Om Prakash, and ably supported by my staff, Anil Kumar, and the crystals were grown in my colleague, Professor Tamilvel's lab. So the first paper came out in 2017. The second one is going to appear too. You can see that, as Grover mentioned, the measurements takes a long time. The bismuth superconductivity were with us for nearly 1 year. Much to the dismay of my student Om Prakash, I told him to do these experiments twice or thrice to verify, because that is the most important thing. The discovery of bismuth gets into a periodic table. So you make sure that it really superconducts and so on. So the second experiment is to look at the anisotropy, which I'm going to talk today, is also important because it tells you the probable mechanism for superconducting. So as I said, the name of the game is to understand whether bismuth will superconduct, or if it superconduct, does it follow a conventional theory. The basic theory of superconductivity is done by Bardeen, Cooper, and Schrieffer, who for that they won the Nobel Prize in 1972. The central idea of the theory is brought from another theorist, Froelich, who suggested that metals can be viewed as a collection of positive ions arranged in a lattice, and the free electrons move there. And what I have shown is an exaggerated view of the lattice distortion. So when the electron moves, the positive charges get attracted to it. So the electron has a positive cloud when it moves. And the convection electron moves through the lattice. So the positive charge cloud accompanies these electrons. And another electron comes at a later date, gets attracted to it. So one can see pictoriously, let's say this electron which is there, which gets moved in this direction, attracts this positive ion. The other electron which comes there gets attracted to it. So it is called electron-electron interaction retarded in time. So the one goes, the positive charge cloud comes and then gets attracted to the other. So this is an attractive interaction as postulated by Froelich, which was picked up by the Bardeen, Cooper, and Schrieffer. So the important consideration there is the electron energy. The velocity of the electrons are about 10 to the power of 4, 5 times larger than the velocity of the ions. So by the time the electron moves out, the other electron can get attracted to it, which is true for all the metals which you have shown in the periodic table, but not so for bismuth. Bismuth has an electron energy which is comparable to the lattice energy. That's where the problem comes, which I will come to it a little later. So let me just give a simple introduction to the solid state physics, which you know. So we know that in metals, at least at absolute zero, all the energy up to EF is filled and the rest is empty. And this Fermi energy is, given in terms of the Planck's constant and the mass and also the number density of the carrier concentration. The typical values are for lead, it is 9.5 and it goes to 10.2 electron volt for aluminum. And for bismuth, you see it's 25 milli-electron volt. The other concept which is important is that when you talk about Fermi surface, for the physical properties, the electrons near the Fermi surface are the ones which is going to contribute, and that we define as this density of states, the allowed states within the certain energy interval. And you see that at finite temperature, the electrons get excited from let's say from the Wells band to the conduction band, and they are the ones who are responsible for many of the electronic properties. And this density of states goes as the square root of E. So this was the state before BCS came into the picture. So before BCS, it was Leon Cooper who said that suppose you have a Fermi surface and you have some electrons which is excited out of it. Suppose there's an attractive interaction between the electrons. The way Froelich has said, what happens to this Fermi sea? He said the Fermi sea becomes unstable, and it is more favorable to form two electrons which are paired at minus p with a momentum minus p and plus p. And so this is called the Cooper pair, the Brown. So it's named after his inventor, so Cooper pairs. So what BCS took was, he developed a theory for the two electrons. They developed a complete theory for this 10 to the power of 22 electrons, which you mentioned. So what I've shown here is again exaggerated view of a shell around this Fermi surface where you have an attractive interaction and there is no interaction outside this Fermi surface. And so using this, the theory predicted a transition temperature of a superconductor in terms of some known parameters. Theta d is the temperature, N is the NEF is the density of states, which is related to the electron phonon parameter lambda, and what is something known as the screen Coulomb parameter. So you know that electrons have like charges and they repel each other. But in a collection of 10 to the power of 22 electrons, there is a screening, and that is what is known as the screen Coulomb parameter. And the important thing here, the basic assumption in BCS is that the Fermi energy is very much larger than the lattice energy. So the theory will break down when you try to apply for a system where the Fermi energy and the lattice energy are comparable. The important prediction of the BCS theory for which they got the Nobel Prize is the prediction of the energy gap, which is delta. 2 delta by kTTC is 3.53, which is the universal prediction. And this energy gap was later discovered by Haber and other people. And so the Nobel Prize was awarded to them. So let's use this BCS theory and do a back of the envelope calculation for some simple metals. For sodium, we know what the theta d, we know what the electron proton coupling constant. You see that you get a temperature like 1 nanokelvin. For aluminium, you see if the calculated temperature is 2.5, whereas the measured one is 1.2. And lead is 10.2 and 7.2. Magnesium, it's predicted to be 30 millikelvin. Unfortunately, it's not superconducting at 100 microkelvin. There are different reasons for it. Important thing is that if you see, in aluminium, it's not very bad. See, BCS theory had lots of assumptions. It's naive to expect that the theory will correctly predict the transition temperature. So many of the experimentalists were disillusioned because they couldn't predict. I mean, the point is that it is great. The theory is great because it is on the right ballpark, and also, it explains how the superconductivity has come. So I don't think we should expect more than this agreement. But for bismuth, where the lattice energy is comparable to the Fermi level, the theory predicts that it should be at 0.2 nanokelvin, whereas the experiment I will show you, it happens at something like 500 microkelvin. So, of course, as I said, you should not apply the BCS theory because the mechanism of superconductivity in bismuth is very, very different from the electron phonon interaction which I am telling you. Anyway, bismuth has been studied for more than 100 years. Many of the solid state textbook phenomena came from bismuth. Large levantism, Seebeck effect, Nernst effect, Kapitsa's law, Shevnikov-Diaz 1-alpha effect, cyclotron resonance, oscillatory macrorestriction, you name it. All these basic phenomena first discovered in bismuth. In the 70s and 80s, there was a lull because people thought that they understood all about bismuth. So it turns out that is not true. The new phenomena of exhibited by bismuth came into fray. Metal insulator transitions, phase transition of Dirac electrons, non-degenerate metallic states, and bismuth phase diagram in the extreme quantum limit, field-induced polarization of Dirac values. There are a host of things. I cannot explain all of this today. You assume that the bismuth has a special place in the periodic table. The most interesting one is that bismuth, what we thought is a stable element, has a alpha decay with a half-life which is 1 billion times even older than the age of the universe. So for practical purpose, you can think as bismuth is stable. So bismuth, as I said, is a unique element. Carrier concentration is small, but it goes by a factor of nearly 10 when you cool this bismuth element or metal. It has a small Fermi surface. It's just 10 to the power -5 of the Brillouin zones. And that's why it has a low carrier density. low Fermi energy, small effective mass, very large free bulk. It's 2 micron at 300 K, and it's of the order of 5 to 6 millimeters at 2 Kelvin. So these are really unusual properties of bismuth. So how does it compare its cousins, other semimetals like antimony and arsenic? Antimony and arsenic are also semimetals, but their carrier concentration doesn't change like bismuth. For silicon, it changes. That's because of extrinsic effects. So why is it bismuth behaving that way? So let's go back to the atomic physics. Look at the outermost electrons of bismuth. It is 6h2, 6p3. So what you have put is the energy level diagram. So when you bring two bismuth atoms, they undergo dimerization. What you should have had is some sort of a Fields transition, that it should have been really an insulator. But the nature doesn't do that way. There is a Fields distortion. So in the structure, instead of FCC lattice, it goes into a rhombohedral structure because that is the most energetically favorable thing. And it has this very unusual band structure. The top of the valence band is, above the conduction band. There is an overlap of the conduction band and the valence band, which I will come to it later. So this is the stable configuration of the rhombohedral bismuth, which has its unique band structure, which I will come to it. But before we go to, band structure and all that, we must ask the question, where is bismuth a metal or a semi-metal or an insulator? The best criteria is what is known as the Mott limit, which works in a variety of oxide, chalcogenides, semiconductors, metals, and so on. What Mott said was, if an expression like A star e to the power of 1 by 3 is greater than 0.26, then it's a metal. Where A star is the effective Bohr radius, A naught is the Bohr radius, epsilon r is the dielectric constant, m naught is the effective mass, and me is the electron mass. So you plug the numbers for bismuth to see that this ratio A star is of the order of 34. So it is in the metallic range. But one unique thing about bismuth is that, as I said, since it occupies only 10 to the power of -5 of the Brillouin zone, one convection electron is shared by 100,000 bismuth atoms. That's because of this low carrier concentration. So the band structure of bismuth, as I said, the top of the valence band here, it's higher than the bottom of the conduction band. So there's an overlap of the conduction and valence band here, and most of the peculiar properties of bismuth is coming because of that. One good thing about bismuth is that most of it have been studied for nearly 40, 50 years. Everything is known about electronic properties, Fermi surface, everything is known. It so happens that, in this 10 to the power of -5 of the Brillouin zone, there are two hole pockets here. So these are the two hole pockets, and these are the 3 electron pockets. So this is what the properties of bismuth, hinges on this electron and hole pockets in the system. And so what we decided to grow this bismuth crystal, and that can be grown very easily. Actually, you can do it even in air. Of course, the quality of the bismuth will not be that good, but it grows very nicely. You can grow very large crystals and so on, as we did it in the Tamil lab. This is the orthorhombic rhombohedral structure of bismuth. And once we do this, and you see that very shiny crystal which comes from there, you can align it with a single crystal diffraction, and you can measure the transport properties. But before that, you do crush the crystal and see whether the X-rays are matching with the standard ones, also see a Loewe pattern of the crystallinity. And before we started working on it, a lot of work has been done on Prisma, but it's always under some pressure. It has a large number of transformations, 3.9K at 26 kilobar when it goes to a monoclinic structure, 7.2K at kilobar when it goes to a tetragonal structure, and 8.3 40 kilobar when it's cubic. So the superconductivity is there, but only under pressure, or in amorphous form and thin films it is there, or granular nanowires it is there. So in all these cases, because the structure has changed, the band structure has changed, the carrier concentration shoots up, you are not, measuring the pure bismuth in its rhomboedral structure with the low carrier concentration. So the BCS theory can account for many of these properties, and people were happy about that. But then people decide, not only me and people, for instance, at Helsinki, they really look for superconductivity of ambient pressure down to 10 millikelvin. That was in the early 90s. And then they gave up that it is not going to superconduct. So we decided that we will, once we build the nuclear refrigerator, we will search for the superconductivity even below 10 millikelvin. So I will show you that it is possible to see the superconductivity at lower temperatures. But, one of the things is that going to a lower temperature itself is difficult. Going to ultra low temperature is very, very difficult. So standard way to cool, go down to 4.2K is liquid helium. It has a boiling point at 4.2K. Pumping over it, you can go down to 1.2. Cooling with liquid helium-3, it has a boiling point of 3.2K. Pumping over it, you can get down to 0.3 Kelvin. If you want to go very low temperatures, we need to have what is known as the dilution refrigerator, whose basic principle I will just tell you. Okay. Then if you want to go well below 4 millikelvin, you have no option to go to adiabatic nuclear demagnetization. So what we have achieved here is about 40 microkelvin. This is the electrons and the lattice temperature. The nuclear spin can get decoupled to it. You can cool down to about 0.1 nanokelvin for nuclear spins. Of course, I am talking about nuclear refrigeration. You can achieve even much lower temperatures of the order of picokelvin while there's a cooling. Those are, different things which I will not be able to talk about this meeting. So what is the roadmap for my next series of talks? So I will talk about the principle of dilution refrigerator, then talk about the adiabatic nuclear demagnetization. Then I will tell you it's not easy. It is not only difficult to produce the lowest temperature, and also we need a sensible way to measure this temperature, that whatever you are measuring is truly a ultra-low temperature. So first let me start on pumping out the liquid helium part. So most of the things, helium-4 and helium-4 and helium-3 I mentioned. Helium-4 you can get down to typically 1.2 Kelvin. After that the vapor pressure becomes very small. Same is the case for the helium-3. And so we need to have a different technique to go below this. So this was what is known as the dilution refrigerator. It was proposed by a theorist, Heinz London, in 1950, then demonstrated by Kamerlingh Honors Lab in 1964. So what is the basic principle? You take helium-4, superfleet helium-4, and add helium-3 concentrate. Helium-3 is an isotope, and you see this superfleet transition comes down as you add more and more helium-3, and then at some point below 0.8 Kelvin, it spontaneously separates into two-phase mixture. One is poor in helium-3, another is rich in helium-3. So the important thing is that suppose we are able to pull this high energy helium-3 atom across this surface of helium-3, helium-4, one can achieve cooling. I mean, that is what is the basic principle of a dilution refrigeration. So in a normal helium-3, what do? You connect the helium-3 bath, pump over this, evaporation under reduced pressure, this system cools down. And then you put this gas which is coming through, cool it by another pot one filled with helium-4, 1.5 K, and then you can have a continuous helium-3 refrigerator. But then for the helium-3, helium-4 mixture, you have a dilute helium-3 atoms, which is here floating on the helium-3, helium-4 mixture. How does one pull this helium-3 from this? No pump at room temperature can do that. So what people have realized is that they use so they use what is known as the still. So this is kept at 0.8 Kelvin. Here the vapor pressure of helium-3 is still larger than the vapor pressure of helium-4. Suppose you are able to reduce the vapor pressure of helium-3 by osmotic pressure, the helium-3 gets pulled across this, and then the warm helium-3 moves inside, and this causes the cooling. And the osmotic pressure can be as high as 1.2 meters of liquid helium-3. So it's able to pull this helium-3, and then this helium-3 which comes to the pump gets back into the system. So you have a continuous refrigeration. So cooling is done by moving helium atom from the liquid to gas-like phase. To remove helium atoms from the mixing chamber, one needs to still around 0.6 to 0.8 Kelvin. So 90% of the helium gas is coming from here to the pump, and that being recirculated again. So one can reach about 3 to 5 millikelvin at the mixing chamber at the bottom. So what we did was we of course bought this liquid dilution refrigerator from Light & Cryogenics. It has a helium dump of 176 liters and 600 liters of helium-4 and 170 liters of helium-3. And of course, you will see only a quarter of a liquid of helium-3 and 860 cc's of helium-4. So this is the massive system. We have, this is another point which some of them I would like to state here, because most of the ultra low temperature app you will see in the world, they have a special building built for themselves and so on. So TFR, we didn't have a luxury. So what we did was to build the system in a ground floor lab, but shielded this system both from vibration and the electromagnetic radiations. So the instrument housing, it's a massive cryostat weighing something like 600 kg, sitting on the optical bench, and then it is you have sand-filled pillars to isolate the system from the vibration, and the cryostat is shielded by special material for the electromagnetic radiation. So that is what the system is. So the dilution fridge gets you to 3 millikelvin. As I said, if you want to go well below 5 millikelvin, you need an adiabatic demagnetization of EPS phase. To understand what is adiabatic deionization, we can just go to the right side of my presentation where I'm talking about vapor cycle refrigeration. What you do there, you take a gas at temperature T, put a pressure and squeeze it. So there will be a temperature rise because you're squeezing the gas, and somehow you take an external medium to remove this heat of formation, and then you have the gas at this temperature T and the initial pressure at P, then you release this pressure. So then there is a drop in the temperature. So that is the vapor cycle refrigeration. Same thing you do with the spins. Now you are talking about nuclear spins. They are pointing random direction at high temperatures, apply a magnetic field, orient them along the magnetic field direction. There is a heat of magnetization, delta T, that you cool it with the dilution refrigerator to take this heat out. So then you get back to the temperature T with the field at the field, finite field, and then you do adiabatic demagnetization. Then you will see that the temperature cools down, and that is called the magnetic refrigeration. Typically, people have achieved of the order of 1 microkelvin with platinum, 10 microkelvin, 50 microkelvin at with copper nucleus lengths. So how does one do that? And you can see so you can see what you have is an entropy as a function of nucleus spin temperature. So you start at 10 millikelvin and at 8 Tesla, apply the field and then you cool the system with dilution fridge, then do a demagnetization. Stop at 8 millitesla, you will reach something close to 10 microkelvin. So how do you do this practically? So let's say you have a superconducting magnet, and let's say you are doing a demagnetization of copper. So what you have is the copper chamber here, copper stage here, and that is connected to the dilution refrigerator by a superconducting switch. Superconductor is a material whose resistance is zero, but its thermal conductivity is very bad. And suppose you make the system normal by applying a magnetic field, you know that the magnetic field destroys the superconductivity. So typically we have an aluminum switch, you apply a magnetic field, make the aluminum switch normal, do a magnetization. As I said, this heat of magnetization is carried out by this, cooled by this dilution fridge, which is operating at, let's say, 5 to 10 millikelvin. Then once the heat of magnetization is removed, then you make this aluminum superconducting, switch off the field. So then it's like a thermal insulator, cuts off this stage from the dilution fridge. So you do a demagnetization as you do here, the stage cools to about 10 to 50 microkelvin.
Professor Ramakrishnan,
Yes,
can I interrupt you at a moment?
right, please.
I think this method will always have limitation of lowering the temperature because the intrinsic interaction will be always a problem.
Yes.
So
Yes,
why not follow the atomic collision path, which is used in the dilute gases?
Yeah, see the point here is that you cannot use that for refrigeration. You can cool the gas of atoms to any temperature you want using 6 lasers, but you can't use those things to cool materials. See, we want a nuclear refrigerator. Our interest is not to cool it to a very lowest temperature. Our interest is to cool nuclear refrigerator. It can be cooled for any material of our investigation. Of course, it is limited by the dipole-dipole interaction.
Yeah.
Okay.
But suppose
So
it
that's
cools
the reason.
by that process, will you get some new phenomena in this? Or
Yeah, see, suppose you want the laser guys can cool rubidium atoms and whatever they want to do, but suppose I want to make, I have a material like samarium boron 6. I cannot ask the laser guys to cool that material. They can't. You see, normal materials which alloys and crystals which come and you want to investigate its properties, that cannot be done by laser cooling.
okay.
Laser cooling is good to look at individual gases or a mixture of gases.
Bismuth can be cooled.
Yeah, bismuth atoms, you cannot cool a complete solid of bismuth. You can vaporize bismuth and bismuth atoms can be cooled.
Bismuth
but the solid
atoms,
state phenomenon
collection
happens
of bismuth
at
atoms.
much larger concentration. Yeah, much larger concentration. If you want to look at it, you need to,
But will that give you some new idea, new physics?
we don't know. Yes, possible. It is possible.
Okay.
The point is that cooling bismuth atoms is going to be much more difficult. I mean, people are, still sticking to the alkaline and things of those things, and not at, higher which requires slightly higher temperature than the alkali metals.
Because
it's not
most of the
but
condensed
yeah, the rate at which they are progressing, I'm sure there will be more interesting thing will come. So What
Oh.
I am telling you is this kind of refrigeration which we provide can investigate any material. Yeah. Okay. So the point here is that we use this dilution fridge. We cool this 5 kilograms of copper down to about 40 microkelvin. I will tell you that. So as I mentioned, there is a superconductor switch, which is made of aluminium. And I told you that it can act as a thermal insulator, basically because you see this graph, which is the thermal conductivity as a function of temperature. You see that for copper, it still remains a good thermal conductor down to very low temperatures. Look at aluminium. Initially, they are comparable to copper, but once it starts superconducting, there is a 5 orders of magnitude reduction in the thermal conductivity. That's how it acts as an insulator. So, which is good for us to keep them link it from the nucleus stage, and that's why we use aluminium as the superconducting switch. It's not enough to produce such low temperatures. We need a reliable sensor to measure it, and most of the sensors which works at fairly higher temperatures, let's say 4K to 100K, will not work at low temperature. The best one works is one is known as the noise thermometer. The other one is the platinum NMR, which works down to about 10 microkelvin. So use the nuclear susceptibility measured from NMR to measure its temperature, and the noise, which is measured ubiquitous noise in every resistor, can be used as a measuring sensor. How does one use this? This is a beautiful concept came out of non-equilibrium StatMech, found by Nyquist, and the experimentalist who did that is what is called as the Johnson. It's also called Johnson's noise, who gave the expression that the mean square voltage fluctuation caused by the thermal agitation of electric charges in an unbiased conductor, it's proportional to T and the resistance R and delta F. This is the frequency spectrum in which, and this sensor works from 4.2K to 1 milli-K, which is available commercially. Because we have extended the range down to about 600 microkelvin with the time. So what we do here is you have a resistor which is inductively coupled to a superconducting transformer, and which is again coupled to a SQUID, superconducting quantum interference device, which is act as a current amplifier, and you can measure the noise spectrum, which is given by this expression, and the noise spectrum at finite temperature, the noise spectrum at the reference temperature, and the reference temperature usually is the boiling point of liquid helium. So it requires only one temperature calibration. You can measure down to 4.2K to 1 milli-K. Then use this noise sensor to calibrate the NMR thermometer. So what you do, the magnetization goes as mx y naught minus T by tau 2, and that is the spin relaxation time, and tau 1 is the spin lattice relaxation time. So by measuring the magnetization at different temperatures and take the ratio, you can also measure the temperature that is used from, let's say, 10 millikelvin to about 1 microkelvin. If you don't know right now, you can ask me later. I can explain you exactly how we measure this. So I'm going to skip that. So we assume that we reliably measure the temperature. Way back in more than, let's say, 10 years ago, we achieved this lowest temperature of 39 microkelvin. Important thing is that you need to keep them long, at least for about 48 hours to do measurements with it. So that is what determines how good is your refrigerator is. So we showed that there is a new window is possible from 1K to 40 micro-K for condensed matter research. So I think the basic operation is not for the faint-hearted, as Grover mentioned, that these are very difficult experiments. You start with liquid nitrogen cooling, then you start the helium-3, helium-4, and helium-3, helium-4 dilution refrigerator, calibration of the thermometers. It is done every run, okay? And after 7 days, if there is no power fluctuations, you will reach about 50 microkelvin. And so when you build a fridge, and that to a state of the art fridge, you want to compare what is happening across the world. Of course, the Helsinki group leads the ultra low temperature field. They have been in the forefront for more than 3 or 4 decades. Then the Lancaster group has reached 30 microkelvin. EFR, we have reached 39 microkelvin. Then there are other facilities across the world, Cornell, Florida, and they are slightly inferior in temperature. Also, the weight of the PSTH is also small. So we set out to do this. We set out to do this because we wanted to reach lowest temperature to study if there is a superconductivity exists for bismuth. One of the problems of these low temperature superconductors is that they are critical field. As I told you, the magnetic field destroys the superconductivity. The Earth's field itself is about 40 microtesla, and that is enough to kill the superconductivity. The previous guys missed it basically because they didn't do enough shielding, and also they didn't want to go below 10 milligauge. So we decided to build a chamber which is a mixture of cryotherm and superconductor. Superconductor is also a very good, shield because it expels the magnetic field. So we made a chamber combining this cryotherm, which has a very high permeability even at 4.2 K. So several layers, and then we measure this field, which is 4 nanotesla. So it's much smaller than the Earth's magnetic field. So that is the chamber in which we are looking for the superconductivity. So as I said, in 2012 we perfected the technique of reaching the microkelvin, but it took 4 years to build the magnetometer to make this magnetization measurement and to measure the magnetization of any material which can be cooled down to such low temperatures. So of course, this involves connection of squids. So the basic squid, of course, we bought it from outside, but the complete magnetometer integration, everything was done by my student, I think, Prakash. It took about 3 years to build this system. And what you see here is the nucleus state, which is at the bottom, and the magnetometer, everything is coupled to the mixing chamber, and the sample is attached to this nucleus stage, and the pickup coil comes to the squid, which is mounted stairs in this system. And so what you see here is a silver step, which is shown here in the third graph, and the bismuth crystal, which you see here, is a very long crystal, because we need to have the connection to the silver should not affect the superconducting properties of bismuth, so the coil is kept far away from there. So, as I said, how does one do the diamagnetism or discover the superconducting transition? At high temperatures, when you apply a field, the field penetrates, and then when it goes to a superconducting state, it expels the magnetic field. So if you measure the susceptibility as a function of temperature, you see a sharp drop, and that is the piece. So when you build a magnetometer, you have to check whether it works, and we did it with rhodium, which we see that it's about 325 microkelvin. This was discovered by mentor Frank Pobel, as I said, more than 40 years ago. And then, so our data matches with Pobel's data. So we are sure that our micrometer is working very well. And then we decided to look for 2 crystals of bismuth with extremely large residual resistivity ratio. The residual resistivity ratio tells you how good is your quality of the crystal is. So it's comparable to the best available which we have grown, the 620 RR and 630. And important part is this discovery of superconductivity. You see that field and zero field cool shows that it's something like a type 1 superconductor. And that when you have a magnetic field, zero field is this. As you apply more and more magnetic field, the superconducting transition gets suppressed as the phenomena of superconductivity. And you see that, you see a graph like this, where the critical field, which we estimated to be about 5.2 microtesla. So if you do this measurement without shielding, Earth's magnetic field is about 40 to 50 microtesla, which will just simply kill the superconductivity. You are not going to see this. So everybody said, as I said, initially the transport, the resistivity goes to zero. The resistivity is not so easy to measure. As you can see that, even down to, this is our latest measurement, down to 15 millikelvin. Nobody has measured below 20 millikelvin anyway. So the point is that the resistance is extremely small. It's of the order of nano-ohms. So when you have something which is at nano-ohms, and you can't pass large currents also, because the heat cooling power of these at the microkelvin is extremely small. It's about 5 nanowatts. So the point here is that you cannot use conventional. This is done with the dilution fridge, so you can measure using squids, and you see that the normal properties itself is changing at something like 0.6 Kelvin. See, initially it shows the t-square dependence, and then it deviates strongly here. You see it at something like 0.6 K. So something happens to the normal properties of bismuth at 600 millikelvin. And that is the reason why it is superconducting at low temperature. Only theories can tell. Of course, theories wants to measure down to lowest temperature, which is what we are trying to do. That's what we are trying to do at recently. So now, once we have established the superconductivity, let's look at some of the theories. Okay, superconducting theories can be classified as phonons, non-phonons. Then you have for phonons this Eliasberg theory, which tells you the superconductivity of transition metals which have large electron phonon coupling constants. The phonons can be adiabatic or non-adiabatic. So the adiabatic ones, we know that it is going to be non-adiabatic because the thermal energy and the electronic energy are comparable. Lattice energy and electronic energy are comparable. So there are several models which predicts for this. The best lowest carrier concentration superconductor before our discovery of bismuth is the strontium titanate, which is an order of magnitude higher than ours. And there are several models which tries to tell you that it is completely not the BCS, it is some other mechanism. The mechanism is still not settled even in strontium titanate. So bismuth, when our paper got published in Science, many theoreticians were involved. I mean, many models have been put forward, including Professor Bhaskaran, using resonating valence bond. But the best model which we feel is by Patrick Lee and his postdoc, which talked about stream electron-electron interaction as the basic mechanism for superconductivity. So another 3 years passed. Now we have done the anisotropy of bismuth. We can see that the anisotropy is very large, but if you compare the critical fields, we feel that the holes. Bismuth is a compensated metal with equal number of electrons and holes. The effective masses of the hole are slightly heavier than the electrons, and we feel that the holes are responsible for superconductivity, which is what Patrick Lee and his postdoc were saying. As I said, more measurements have to be done, and we hope that this would be taken up by others. So the summary is that bismuth displays unconventional superconductivity and requires a theory which goes beyond the model of superconductors. So what is the way to measure resistance well below 10 millikelvin? The only way we can measure is, as I said, measure the noise. We said we are using the noise as a thermometer. So reverse this. You measure the noise with a noise thermometer, but you measure the resistance of the material using the same technique. And then from the noise, because you are not putting any current into the system, so you can try to measure the resistance. And this has been done for the ytterbium rhodium 2 silicon, which I mentioned, by the group in England. We are trying to get a collaboration with the Magnion group in Germany to do these measurements for the bismuth. Then the question is anisotropy. I showed you one anisotropic measurement. Since the bismuth is rhombohedric, we wanted to check along the axis how the effective masses change and so on and so forth, and what is the critical field which it gives. And can we see superconductivity and antimony and arsenic, which is also a semi-metal with a comparable concentration. So the question is, are we seeing beginning of a new class of superconductors? So I only took one topic, that is the superconductivity at ultra low temperature in bismuth. So which forms into this first question, what is the fate of metals at low temperatures? I didn't touch upon the granular superconductivity in materials like platinum, which also requires some millikelvin and sub-millikelvin temperatures. The exotic phase transition of the realm of unknown superconductivity in pure bismuth, does it happen only in pure bismuth, or is it happening in antimony, arsenic, and other semi-metals as well? There are many more. I mentioned samarium boron 12 and rhodium B12, ytterbium B12, and so on. So the important thing is that many of the properties of phase transitions are discovered at low temperatures. Then, our idea of material science, crystal structures, and so on will allow you to push the transition temperatures higher, and maybe they could be used from the technological side when we achieve such a phenomena in practical temperatures. So the superconductivity is one such thing, and so the question for ultra low temperature is just not to produce temperatures, but to use this as a refrigeration to look at, examine some exotic temperatures. So I will stop here and thank you for your patience, and looking forward to some questions. Thank you. Thank you very much.
Okay, thank you, Professor Ramakrishnan, for the nice talk. Now we take the questions first from this WebEx. So you can unmute and ask the question.
I must say that this is an excellent lecture I have heard on low temperature physics. I have heard many. So I must congratulate you for this lecture. I have a couple of queries.
Okay.
You did mention about the non-Fermi liquid behavior at some stage.
Right.
Do you have observed in your experiment somewhere non-Fermi liquid signature in the superconductivity?
Yeah, not in bismuth. For instance, we also done measurements on ytterbium, rhodium to silicon 2. So there, the electronic specific heat, which is supposed to go as gamma T, doesn't do that.
Okay.
It has a divergence at that temperature. So, and the electronic susceptibility, we know for the simple Fermi liquid how it behaves, it doesn't do that way. So this is a system which clearly shows non-Fermi liquid and then goes to a superconducting state at 2.5 millikelvin. So there are few other things which are now coming to the state, and people are wondering what kind of mechanism, what is the glue? Electrons have to get paired to do a Meissner effect or superconductivity. But what is the glue? For the DCS, the glue is phonons. For these materials, it's still not true. I mean, the major cousin is the ITC. Even there, it's still a debatable question depending on which part of the spectrum you are there, underdoped, optimally doped, higher doped, and so on. So the non-Fermi liquid has been there in some of the superconductors. But bismuth, we don't see that yet because the properties are difficult to measure. The specific heat, for instance, is difficult to measure below, let's say, about something like 100 millikelvin, because the nuclear heat capacity, the quadrupole nuclear heat capacity of bismuth is extremely large and much larger than the electronic one. So it's very difficult to do the heat capacity measurements and to show that, whether there is a non-Fermi liquid thing exists or not in this.
But in the density of states, because you do have some clue about density of states, which explains your data. So does
Right.
that show some anomalies? The density of states are like a non-Fermi liquid.
It's the problem. The problem there is that you need to go to very low temperatures. So the bismuth, the nuclear quadrupole comes in the way to look at the electronic contribution. So that is the reason why in bismuth people have not discovered any non-Fermi liquid elements. But the transport shows that the electronic properties are changing because bismuth used to have a robust T-square dependence at low temperature due to Barber scattering. But below 600 millikelvin, what we find is that it doesn't show a T-square dependence. In fact, at very low temperatures, it behaves like a Bruneian. You can fit this T2 profile very nicely. I just showed you the graph briefly. So, but it's not very clear as to what kind of electronic mechanism operates. So something is changing in the normal state. But the theoreticians want what is the resistance just above its superconducting state, which is which can be done, but it just requires the noise thermometer measurement, measure the resistance using noise. And that's slightly tougher at this stage, but it can be done. I mean, my former student, Om Prakash, is now with the Halloway group in UK, who is now learning the NMR as well as the ultra low resistivity measuring ultra low noise. So hopefully he will come and set it up at some point.
And I thought you have gone to the microkelvin temperature range, is it?
Right.
But then
40
how is is there any error introduced there? Is the limitation?
Yes. All the temperatures have about 2 to 3% error in this.
Oh, only that,
And,
but that's very small then.
Yeah, so it's not very high because we always test. See, the only point to test your thermometry is with respect to some fixed points. So luckily, we have this Pobel's, my mentor's superconductivity rhodium, which is around 325 microkelvin. So when we use our thermometer to check that, we were able to measure within 2 to 3% of that. So it gives us some confidence that we are measuring.
But is there
Right.
some
Only-
other than bismuth? Is there other than bismuth where non-Fermi liquid behavior will be prevalent more than?
Yeah, so samarium boron 6, which I said.
Okay.
So, this is another candidate for the non-Fermi liquid, and also people are talking about topological insulator and so on. There is a very nice theory by Polman which suggests that it should superconduct by something like a few hundred microkelvin, so about 700 microkelvin. We cooled that. So we had the best crystal from Geeta Balakrishnan from Warwick. So we cooled that, and we just couldn't see anything down to 100 microkelvin, much to the dismay of the theoretician who then came to my lab and said, so he was very curious how we are measuring, and he wanted to make sure that we measure the right temperature, and then he left away slightly dejected. So I told him to do his theory and then see, maybe you push it down, then we will come sometime to measure it. So the measurements of the temperature are accurate, but the basic problem is that you have to make sure your sample cools. Sometimes the thermal boundary resistance between the sample and the nuclear stage is so large that it cannot be cooled. I mean, we had this experience with titanium beryllium 2. This is another interesting material which is supposed to show higher angular momentum pairing, what is called the P-wave pairing. I showed you the standard BCS where you have plus K, which is minus K, that's opposite momentum element, they are paired. But these are parallel moments, so it's a strong candidate. So we cooled the fridge to about 40 microkelvin, but we find that the sample is at 10 millikelvin. And then we looked at the relaxation. It will probably take a few years for it to come to such lower temperatures, to the temperature which our interest is. So we have to abandon that experiment. So
Very interesting.
it can happen.
Very interesting, actually. By going this method and observing things, it's very exciting. we do some computer simulation experiments,
Right.
and there we observe non-Fermi liquid behavior very often in the correlation functions, but we don't observe any macroscopic properties like you are measuring. So therefore, we doubt there whether these really exist or it's there only on a model or something like that. In the real system, whether it exists or not, non-Fermi liquid behavior. That's a kind of feelings I get it.
No, I think the well-documented things are there right now. There are, as I said, ytterbium rhodium 2 is a celebrated example. There are other superconductors we do so non-Fermi, measured by us and measured by others also.
Okay.
So any other question one can unmute and ask directly before we take up the question from the chat box.
Ramki, this is Vinod. Can you hear me?
Please.
No, compliments to you. To me, your talk essentially captures the spirit of Professor B.M. Anand. And in view of what Manmohan said initially, see, this is not something which you can do on the basis of a bought out item and then do some experiments. You struggle a lot, build things from scratch. And I think this is what would have pleased Professor Anand if he was listening to your lecture. So compliments, I think, carry on that great tradition. Yeah. Of course, it is hard, but congratulations.
I also,
I just want to mention that, Professor B.M. Anand is far ahead. I just looked at this thing, thanks to Rajendra Singh and his literature. There was a measurement which he did in 1953. And that data was taken at 2011 by another group and tried to analyze this. I mean, imagine the precision in which he has made that data and got this data, which is used after 58 years. I mean, it is mind-boggling. I mean, this is something which nicely brought out in that thing which Grover has sent it to me. I mean, the kind of precision he had at measurements. It is, this is every experimentalist should be trying to do this. I mean, you see that somebody has already shown you an Indian and difficult conditions, showed this, and that is what every experimentalist should emulate. At least try and see whether you can reach. Yes. Maybe he has shown you the way, and amazed. I'm really simply amazed.
I really endorse Sani's view that, in fact, what I hear from my colleagues at that time, old days, when I joined in 70s, that he was very fond of doing things in the laboratories. He was not bothering about research work at all. He dedicated all times to the teaching students and making instruments in the lab, in the workshop. He had a very good workshop in Punjab University. So he made various instruments to teach the physics to the BSc and MSc students. So you have got the spirit of that and captured and presented very well in this lecture. I also compliment you.
But Vinod, this kind of experiment can go on only in TIFR. You cannot do these things in the Indian universities anymore.
You're absolutely right. No,
because
I
will support a university professor the way TIFR supported.
Well, I don't agree. I don't agree with Arun Grover. I don't agree with any Arun Grover. It can be done anywhere. There's a person like.
The point is, you need support. You need money. You need money without asking questions.
That's not the issue.
This is not
money without asking questions. Professor Pathak, please understand, I have witnessed
I have witnessed many things.
5 crore. Who will commit 5 crore rupees without asking questions?
Just 1 second. I have a request.
There is a way. That's it. Let me not go much more detail. I think.
I don't want to add to cacophony. I just want to make one point.
People don't want to go to university. That's the problem.
The fact that you have ensured that I have actually even the book on Ruchiram Sani, which in a way captures, the traditions of Government College Lahore, which finally Professor Anand brought to Chandigarh and so on. Now, this is another debate whether or not enough funding is available to people who even have a certain amount of enterprise in them. That's another issue. But I think what I was trying to compliment Ramki was, here is a person who is trying to put together on the basis of his toil. And this is what would have pleased BM Anand. I'm not getting into a discussion. It may require funding, which may or may not be forthcoming and so on. Otherwise, Punjab University should have built some accelerators and so on. So that's a separate debate. But I think at this moment today, on this occasion, we should actually enjoy the spirit of Professor Anand and compliment Ramki.
So that's
for having
correct.
toiled. Maybe it has been done only in TIFR. It will be hard to replicate it. Maybe not even in TIFR because it requires TIFR and Ramki.
Raki, that's what I
And
say.
it also requires good
it requires
crystals.
person.
And we had
Absolutely.
we got Tamil Vale as a crystal grower in TIFR at the recommendation of a theoretician
Anyway, I
named
think
Bhaskaran.
we should
And
not
how much of
discuss.
struggle we had in
Grover
inducting this
Saab,
person
we
and,
should not discuss.
convincing the TIFR administration that we need a crystal grower like this. That crystal grower will combine with Ramki 20 years down the line, and then this will come out.
I think let us
Sure.
celebrate this very beautiful lecture of Ramakrishna, not debate on this. What can be done, what cannot be done. Leave it in there.
You see,
Leave
the
it
point
there.
is there
I think
are
Manmohan,
challenges.
please conclude it. That's it.
Okay.
Yeah,
I
I
think
was just,
there are
I just want to say
questions.
one thing. I just want to say one thing. As Arun pointed out, I think high quality crystals are a must, especially in bismuth, because the editor of the science, she wanted, I said, we have the 6,9 pure bismuth, and she's still not convinced. Then we have to do an elemental analysis to show that every impurity is below 10 ppm. This also have to be done. And then she said, you see, and finally, as a good gesture, they waived all the publication charges. So, that is something good of them for this paper. And the one thing which she said was really strikes me. She says, I have to do this because this gets into a periodic table. We have to be very careful. So that was his last comment of the referee, which must have conveyed to her. So unless high quality crystals come, it is very difficult to work with, at these temperatures and so on. Because any small impurities will be creating havocs when you cool below 10 millikelvin. So,
Okay, thank you. So we have
yeah.
few questions from our BSc undergraduate students, which is in the chat box.
Sure.
Yeah. So Bhavya Jain, she asks, sir, what is the behavior of superconductors in nearly vacuum area or outside of the earth?
So the superconductor will remain superconductor, whether you are in Earth or elsewhere. Only thing is that, some superconductor like bismuth, if you don't shield it from the Earth's magnetic field, it will become normal. But outside, it will become a superconductor because there's no ambient magnetic field. So the nature of the superconductivity will not change, whether you are here or elsewhere.
So the next question by Dr. Deepak Kumar. We hear news of room temperature superconductivity from Ranga Group at Rochester and some Bangalore group as well. Please comment.
Yeah. See, the Bangalore group, it's difficult to, they have not shown it fully, so it's still a question mark there. So I don't know. Whereas the other one at high pressure, it's the genuine result. So what you do is that this is all started with some theoreticians long ago showed that if you squeeze hydrogen, we know that it becomes hydrogen gas, it becomes a metal. And they predicted that it will become a superconductor because it's Debye temperature. If you look at my formula, it is proportional to the Debye temperature. So the Debye temperature for the solid nitrogen is of the order of few thousand Kelvin. So the theoreticians thought that we could have superconductivity. People have seen the metallicity of hydrogen at high pressures, but nobody has seen the superconductivity yet. And also this cannot be held for longer time. So the metallurgists thought that any hydride, if you squeeze, you probably would get superconductivity. And this was pioneered by the German scientist, and he squeezed about 10 years ago now, more than that. And so hydrogen sulfide, and he could see superconductivity at 200 degree Celsius, so it's 200 degree Kelvin. And then the Rangas thing is that he could, now people started using different hydrides and putting a little carbon on it and so on. The squeeze is 2 million atmospheric pressure. They do see the room temperature superconductivity. But here, the mechanism is again phonons. Because when they replace the hydrogen by deuterium, the TC comes down and it fits to the simple, to the BCS model to some extent. But then it's not completely a BCS superconductor because there are large electron correlations which people have started finding out. So the high pressure superconductivity is a reality. I think you can squeeze and get even room temperature in beyond. But the trick is to have superconductivity at ambient temperature, because then only you would see the large number of applications and so on. That doesn't mean that this effort is not laudable. It is laudable because people wanted to see the conventional theory, superconducting theory predicts that you can't have above 40 Kelvin, because if you have a larger electron phonon coupling constant, the structure becomes unstable. So that is the problem. The one which is squeezed, then you could have a stability. But when you release the pressure, it goes back to a full structure, so you don't see the superconductivity. So important thing, I think world over, that is the game right now. Try and see synthesized material so that you don't have to squeeze it to 1 million atmosphere, let's say 10 kilobar or even less, so that you can achieve the same room temperature superconductivity. And ultimately, the game is, the holy grail is superconductivity at ambient pressure. So that is, well, hopefully it might come. We don't know.
Okay, if there is any other questions, one can unmute oneself and ask.
There was a hand from.
May I
Mr.
ask
Chau.
one question?
Please.
I see some hand.
Yeah, so first of all, thank you to Professor Ramakrishnan for this very nice seminar. So I have a very naive question. You talk about this ultra low temperature and the research in this field. So how this is connected with the field of quantum computing and what kind of effect it has on that field? Can you comment on that?
Yeah, so quantum computing, you need not such a low temperature. Even 10 millikelvin is good enough. Dilution fridge is good enough, because you need to cool the sensors down to such low temperatures. Where I think such an ultra low temperature help is that finding new materials, and which is not working towards the BCS kind of a thing. Let's say bismuth. It so happened that it is superconducting at 0.5 millikelvin. But if one can synthesize materials like bismuth, which could do it at, let's say, 50 millikelvin, that is useful for. So the conventional things are now done with aluminium and in some cases niobium with the computing in the Josephson junctions. But if we can discover material at slightly higher temperature, that would be useful for them. So you don't need microkelvin to do quantum. 10 millikelvin is good enough.
Thank you.
Okay, if there is any questions. So if not, so let's thank Professor Ramakrishnan for this nice talk, and also Dr. Anand and family who are attending this lecture despite the odd hours in United States. So before we conclude, now I request Dr. Sakhi Gautam to give a formal vote of thanks.
Yes, thank you, Professor Behra. Good afternoon, everyone. So I extend my gratitude to our esteemed speaker, Professor S. Ramakrishnan Ji, Director TIFR, for delivering 6th Professor B.M. Anand Memorial Lecture. I thank you, sir, for taking us through this journey of low temperature, which started in Netherlands around 110 years back with Camerlingons, And we, however, missed your presence here, sir, at Punjab University, and we wish to see you in near future. My sincere thanks goes to Professor M.M. Gupta ji, Professor Emeritus Punjab University, for presiding over this event and apprising us about Professor B.M. Anand. I am also very thankful to Professor K.N. Pathak ji, Professor Arun Grover ji, Professor Kia Dharamveer, Professor Suman Bedi, who joined us for this event. We are also grateful to Anand family for joining us, and my sincere thanks goes to Anand Memorial Trust also for supporting this commemorative lecture series. My generous thanks to all my colleagues at Department of Physics for helping us arranging the modalities of this program. And finally, I would like to thank all the students and other participants who joined us for this event. Thank you, everyone.
So thank you all again. And now we can conclude the session.
Thank you.